this lecture, I am going to talk about Ehrenfest's theorems, and they kind of tell you how the expectation values of p and x change with time, and these theorems tell you how expectations value of p and x change with time, and they give it some meaning which we have been sort of anticipating. All right. So, recall that expectation value x is defined as integration psi x t mod square x dx, and we said earlier that this is like the average value of x, and similarly average value of p is defined as integration psi star x t h cross over I d psi over d t dx, and we said this is like the average value of momentum for a particle in wave function psi state. What Ehrenfest's theorem tell you is give more meaning to this and show that p can be written as m x d by dt. So, this is like m v, all right. So, the expectation value of p, that is the average momentum that we have been talking about, is m d by dt of the average value of x. This is first theorem. Second one tells you about the rate of change of p, and that tells you if I take the expectation value of minus dv dx, that is the derivative of potential v with a minus sign in front, which is the force. This is equal to d by dt of average value of p. So, these again tell us that these expectation values as defined earlier when we were talking about equivalence of Heisenberg and Schrodinger's picture do have a meaning of being the average position and average momentum of a particle in state psi. So, let us now prove these. X average is nothing but integration psi star x psi dx, and d by dt of x is therefore going to be integration d psi star by dt x psi dx plus integration psi star x d psi by dt dx. Notice that if we are talking about the change of expectation value of x and p in time, the wave function necessarily has to be time dependent. In a stationary state, these things do not change in time, as we showed earlier, because the probability density is independent of time. Now, I know that I h cross d psi over dt is nothing but minus h cross square over 2 m d2 psi over dx square plus vx psi, and minus I h cross d psi star over dt is equal to minus h cross square over 2 m d2 psi star over dx square plus vx psi star. I can substitute these values in the equation above to get d by dt of x is equal to one over I h cross with a minus sign integration of minus h cross square over 2 m d2 psi star over dx square times x times psi. I will put this in the bracket, plus integration psi star Vx x psi, that is from the first term. So, this corresponds to this term. For the second term, I am going to have minus integration h cross square over 2 m d2 psi over dx square, I am writing d psi by dt, times x times psi star minus integration psi star v x psi psi dx. I have taken I h cross out. So, let us see now, this is perfectly fine, this is except that this sign is going to be plus, yes. So, this is fine. Now, I can cancel the second term, and what I am left with is d by dt of x is equal to I over h cross, 1 over minus I have written as I over h cross, times h cross square over 2 m integration d2 psi over dx square x psi star minus d2 psi star over dx x psi dx. That is what I am left with. So, what I am getting is d by dt of x is equal to I over h cross square over 2 m integration of d2 psi over dx square x psi star minus d2 psi star over dx square x psi dx. Which I can write as I h cross over 2 m integration of, let me take d by dx out, and inside I get d psi over dx x psi star minus d psi star over dx x psi dx. That is the first term. Now, I have to make some corrections because there are extra terms going to appear. So, I h cross over 2 m integration of, I am going to subtract. So, minus d psi over dx d psi star over dx minus or times x minus d psi over dx times psi star minus minus plus d psi star over dx d psi over dx times x plus d psi star over dx times psi integration dx. Now, the first term can be integrated directly, and if psi's vanish at infinity, boundary condition gives you that this is going to be 0. In the second term, these two terms are going to cancel. So, what I am left with is d by dt of x is equal to I h cross over 2 m integration of psi star d psi over dx with a minus sign plus d psi star over dx psi integrated over dx. The second term d psi star over dx psi dx can be written as integration of d by dx of psi star psi minus integration of psi star d psi over dx dx. Again, the first integral vanishes because psi vanishes at large distances. So, what I am left with is d by dt of x is equal to I h cross over 2 m integration of minus psi star d psi over dx dx times 2. This 2 cancels and I can write this as 1 over m integration psi star h cross over I d psi over dx dx, and this is nothing but 1 over m expectation value of p. So, what I have shown is that d by dt of x is expectation value of p divided by m. This is the first Ernst theorem that again tells us that the expectation value of p or expectation value of x can be thought of as the average values of the momentum and position of the particle. For the second theorem, we have to show that d by dt of expectation value of p is equal to nothing but minus dv by dx expectation value, which is the expectation value of the force. To prove the Ernst second theorem, we again do what we did earlier for proving the first theorem, and that is write d by dt of p as d by dt of this expectation value, which is psi star h cross over I d psi over dx dx, and this can be expanded as equal to integration del psi star over del t h cross over I d psi over dx dx plus integration psi star h cross over I d by dx of d psi over dt dx. I have interchanged the partial derivatives with respect to x and t, but that we can do. Now, the next step is going to be write d psi star dt and d psi over dt using the time dependent Schrodinger equation as we did earlier. And you do that and substitute this in the equation, and you get d by dt p equals, after the manipulations and partial integrations and all that, you get this equal to minus dv by dx expectation value, which is nothing but integration of psi star minus dv by dx psi dx, which is the second theorem of Ernst, which tells you that the average value of p or the expectation value of p changes according to Newton's laws. I have not done the derivation here, and I am leaving that as an exercise because it is a very simple derivation, although little longish. So, I will leave it for you. So, what we have shown in this lecture is, to conclude, one, that x and p are related as d by dt of x is expectation value of p by m, and 2, that d by dt of expectation value of p is nothing but the expectation value of the force, which is same as psi star minus dv by dx psi dx. So, this again tells you that these quantities are the average p and average x for a particle in state psi.